Welcome to our deep dive today.
Sounds fun.
We're going to be exploring a really cool concept today.
Oh.
It's called quantum enhanced dimensionality reduction.
Catchy.
Or QEDR for short.
Even better.
You sent us this intriguing essay by Jorgo Schneepat.
Jetpat. Yeah.
And honestly, I'm curious to see what we uncover here.
Me too.
Think of it like this. We're going to take this complex topic.
Yeah.
And we're going to distill it down to the most fascinating and important bits.
Sounds like a plan. It is a fascinating area. What Schneepat does so well is he connects the dots between quantum computing and dimensionality reduction.
Interesting.
Two fields that on the surface might seem totally separate.
Right.
But he makes a compelling case for how quantum computing could be the key to unlocking insights from these huge data sets that traditional methods just can't handle.
Right. It's like he's pointing to this whole new frontier of data analysis.
It really is.
But before we get ahead of ourselves, let's break it down for anyone who's not already knee-deep in data science.
Yeah, good idea.
What exactly is dimensionality reduction? And why should we care?
Imagine you have a giant spreadsheet with thousands of columns.
Okay.
Each representing a different variable.
Gotcha.
That's high-dimensional data.
Okay.
And it's everywhere these days.
It is.
Dimensionality reduction is like finding a way to simplify that spreadsheet without losing the most important information.
So it's about finding the signal in the noise.
Yeah,
right?
Yeah, exactly.
But why is high-dimensional data so difficult to work with in the first place?
Well,
Schneepat mentions this curse of dimensionality.
yes.
And it sounds a bit ominous.
It is a challenge.
Okay.
As the number of dimensions in your data set increases, the data points become increasingly sparse. It's like trying to find a specific grain of sand on a vast beach.
I see.
Traditional algorithms struggle because the relationships between data points become less meaningful.
So it's not just about the amount of data.
Right.
It's also about the complexity that comes with all those variables.
Yeah.
And I guess that leads to practical problems too, right?
Absolutely. Schneepat points out the computational cost and storage issues.
Makes sense.
Traditional methods, even something like principal component analysis or PCA, become incredibly slow and resource intensive when you're dealing with these huge complex data sets.
Wow.
It's like trying to run a marathon with a backpack full of rocks.
Okay. I'm starting to get a better sense of the problem.
Hey.
So tell me more about this PCA thing.
How
does it work? Exactly.
Imagine you're looking at a 3D cloud of data points.
Okay.
PCA finds the lines that capture the most variation in the data.
Gotcha.
Then it projects all the data points onto those lines.
Okay.
Effectively reducing the data from 3 dimensions to 2.
Okay.
It's a simplification, but it preserves the most important information.
So we're taking this complex data set and kind of flattening it to make it easier to work with.
That's a good way to think about it, yeah.
But how does quantum computing fit into all of this? Yeah. I know it's supposed to be incredibly powerful, but to be honest, it still sounds a bit like science fiction to me.
That's where things get really interesting.
Okay.
Schneepat argues that quantum computers can overcome many of the limitations we've been discussing.
Okay.
They utilize these bizarre quantum phenomena to perform calculations in a fundamentally different way than classical computers.
Okay, hold on. Before we go any further.
Sure.
Can we demystify some of those bizarre quantum phenomena? I think we need a little more than it's different.
Fair enough. Let's start with the basic building blocks.
Okay.
Classical computers use bits, which can be either a 0 or a 1.
Right.
Quantum computers use qubits, which can be in a superposition.
The superposition.
Meaning they can be 0, 1, or both simultaneously.
Whoa, so instead of just two distinct states,
Yeah.
it's like this blurry in-between state?
Exactly.
Yeah.
It's like a coin spinning in the air before it lands.
Oh.
It's both heads and tails at the same time until it's measured.
I see.
And it gets even stranger with entanglement.
Entanglement, oh boy.
This is where 2 or more qubits become linked no matter how far apart they are.
Interesting.
Their fates are intertwined in a way that even Einstein called spooky action at a distance.
Okay, that's definitely pushing the limits of my intuition.
It's pretty wild.
But how do these quantum properties actually help with dimensionality reduction? It seems like we've just made things even weirder.
Well, Schneepat specifically highlights something called the HHL algorithm.
The HL?
This is a quantum algorithm that can solve linear equations exponentially faster than classical methods.
Oh, wow.
And linear equations are at the core of many dimensionality reduction techniques.
So it's like we've suddenly got this super-powered engine.
Yeah.
for calculations that used to take forever.
That's one way to put it.
Okay.
And this opens up the possibility of analyzing datasets that are simply beyond the reach of even our most powerful supercomputers right now.
Okay, I'm intrigued. But before we get too carried away,
Sure.
Are we talking about actual real-life quantum computers that can do this today?
Right.
Or is this all theoretical for now?
That's a great question.
Yeah.
And Schnepphat is upfront about the fact that we're still in the early stages of quantum computing.
Yeah, that's what I thought.
We don't yet have quantum computers powerful enough to tackle real-world high-dimensional data sets.
Okay.
However, the theory is solid, and the potential benefits are so significant that it's a field worth exploring.
So it's a bit of a long game, but with potentially huge payoffs.
Exactly.
But assuming we get to the point where these powerful quantum computers exist, what would a world with quantum-enhanced dimensionality reduction actually look like? I know Schnepphat calls it QEDR.
He does, yes.
Did he coin that term?
He did.
Clever.
And he suggests that QEDR could revolutionize fields like image processing, genetic data analysis, and even financial modeling.
Wow, those are some big ones.
Imagine analyzing incredibly high-resolution medical images in real time to assist surgeons during surgery.
Yeah, that would be incredible.
Or unlocking the secrets of the human genome at an unprecedented pace.
Those are some bold claims.
Yeah.
But how do we go from these quantum algorithms to, say, analyzing a medical image in real time? What's the bridge between those two worlds?
Schnepphat dives into a concept called quantum principal component analysis, or QPCA for short.
QPCA?
It's essentially a quantum version of the classic PCA we discussed earlier, but turbocharged by the power of quantum computation.
So is it fair to say it's like PCA on steroids?
You could say that. The key is that QPCA can potentially perform those complex eigenvalue calculations, which are at the heart of PCA, exponentially faster than traditional methods. We're talking about reducing the complexity from O in 3 to O log n. That's a massive difference when you're dealing with large data sets.
Okay, I'm starting to see the appeal. Yeah. But what about those limitations you mentioned earlier? If we don't have powerful enough quantum computers yet, is QEDR just a pipe dream for the distant future?
Well, Schnepphat addresses that too. He's realistic about where we are with quantum hardware.
Okay.
And he suggests that a more immediate path forward might involve something called hybrid approaches.
So we'd be combining traditional methods with these emerging quantum algorithms.
Exactly.
Kind of like a best of both worlds scenario.
Exactly. It's like using a regular car to get to the highway and then switching to a supersonic jet to reach your destination in record time.
I love that analogy. It makes this whole quantum thing feel a bit less daunting.
Yeah, that's a good way to think about it.
But I'm still curious.
Yeah.
Are there any specific examples of how this hybrid approach might work in practice? How would we combine the classical and quantum worlds?
Well, let's take image processing as an example. We could use classical methods to do some initial pre-processing of a huge image.
Okay.
Maybe reduce the resolution or identify areas of interest. Then we could use QPCA on a quantum computer to analyze those specific regions with incredible speed and accuracy.
Okay, now that makes sense. It's like we're strategically using each tool where it's most effective.
Exactly.
But this is already a lot to wrap my head around.
I know, right?
We've covered so much ground, from the basics of dimensionality reduction to the mind-bending world of quantum algorithms.
Indeed we have, and we've only just begun to explore the possibilities of QEDR.
Let's dive even deeper. In the next part,
Okay.
We'll explore Schnepphat's insights on the specific benefits and challenges of QEDR.
Great.
And delve into the potential real-world applications of this groundbreaking technology. All right, we're back and ready to delve deeper into this QEDR revolution. Schnepphat seems pretty optimistic about the potential here. So, beyond just speed, what other advantages does he highlight?
Well, one of the things that really stands out in Yorgo Schnepphat's essay is the idea that QEDR could lead to more accurate analysis.
Oh, interesting.
Especially when it comes to those complex, nonlinear relationships in data that traditional methods often struggle with.
Okay, let's back up for a second. What do we mean by nonlinear in this context? I'm picturing a squiggly line instead of a straight one, but maybe that's too simplistic.
That's actually a pretty good visual. Think about a simple graph showing a direct proportional relationship.
Okay.
That's linear. But a lot of real-world phenomena are much more intricate. The stock market, weather patterns, even the way genes interact, These are all nonlinear relationships.
So those classic methods like PCA might miss some of the nuances because they're built for more straightforward relationships.
Exactly. PCA is great for finding patterns where the data clusters neatly along straight lines, but when the relationships are more complex and less predictable, PCA might not capture the whole picture.
And that's where quantum computing comes in.
Precisely. Schneppat suggests that quantum algorithms, with their ability to exploit superposition and entanglement, could be much better equipped to handle those nonlinear relationships.
Okay. They can explore a wider range of possibilities and uncover subtle patterns that traditional methods might overlook.
So it's not just about crunching numbers faster.
Yeah.
It's about revealing hidden connections and getting a deeper understanding of the data.
This is starting to feel like we're cracking a code. But let's bring it back to real-world applications. Schneppat gives some specific examples of how QEDR could make a tangible difference, right?
He does, and they're pretty diverse. He talks about revolutionizing fields like image processing, genetic data analysis, and even financial analysis. Let's take image processing, for example.
Okay.
Imagine being able to analyze high-resolution medical images in real time.
Yeah.
Providing surgeons with instant feedback during delicate procedures.
Wow, that would be incredible. No more waiting hours for scans to be processed. Surgeons could make more informed decisions on the spot, potentially leading to better outcomes for patients.
Exactly. And Schneppat also highlights the potential of QEDR in genetic data analysis. Think about analyzing massive genomic datasets to identify potential drug targets or personalized treatment plans. The human genome is incredibly complex, and it feels like we've only just scratched the surface of what it can teach us.
That's a field I'm particularly fascinated by. The idea of unlocking those secrets and accelerating progress in medicine is incredibly exciting.
Absolutely. And then there's financial analysis. Schneppat suggests that QEDR could enable real-time analysis of massive financial data sets.
Wow.
Helping analysts make better predictions and manage risks more effectively.
So not quite a crystal ball for the stock market, but definitely a powerful new tool for navigating the complexities of finance. But amidst all this talk of potential benefits, what about the challenges? Are there any roadblocks we need to overcome before QEDR becomes a reality?
Of course. Schneppat acknowledges that there are still significant hurdles. We've already touched on the limitations of current quantum hardware, the need for more qubits, longer coherence times, and overall stability.
Right. We need those quantum computers to be more robust and reliable before we can really unleash their full potential.
Exactly. And beyond the hardware challenges, there are also algorithmic challenges. We need to develop more sophisticated quantum algorithms specifically tailored for dimensionality reduction tasks. And as we've discussed, the development of those hybrid algorithms that can seamlessly integrate classical and quantum approaches is going to be crucial.
So it's not a case of quantum completely replacing classical.
Right.
But rather finding the right balance and leveraging the strengths of each. Schneppat seems to see collaboration as key here, right?
Absolutely. He stresses the need for computer scientists, quantum physicists, and domain experts to work together to overcome these challenges and unlock the full potential of QEDR. It's a truly interdisciplinary endeavor.
It's exciting to think about the kind of breakthroughs that could emerge from that kind of collaboration. But as we move forward, are there any broader societal implications that we should be thinking about?
That's an important point. While Schneppat's essay focuses primarily on the technical aspects of QEDR, the ethical and societal implications of such powerful technology are certainly worth considering.
Yeah, definitely.
As with any new technology, we need to be mindful of potential unintended consequences.
I think that's a great note to end this part of the discussion on. We've explored the potential benefits and challenges of QEDR, and it's clear that this technology could have a profound impact on a wide range of fields. But as we develop these powerful tools, it's essential that we proceed thoughtfully and responsibly.
I couldn't agree more. In the final part of our deep dive, we'll wrap up our exploration of Schneppat's vision for the future of QEDR. We'll discuss the key takeaways from his essay and ponder the broader questions raised by this groundbreaking technology.
Right. We've journeyed deep into the quantum realm, exploring the ins and outs of QEDR.
It's been quite a journey.
It really has. As we wrap up our dive into Jurgo Schneppat's essay, what are the key takeaways we should remember?
Well, Schneppat paints a very compelling vision of the future, where QEDR transforms how we analyze and understand these massive data sets that are becoming more and more common. He really emphasizes the potential of those hybrid approaches, combining the best of classical and quantum computing.
It's like building a bridge to the future of data science.
A very good analogy.
Thanks. But Schneppet doesn't shy away from the challenges either. What are the biggest hurdles that need to be overcome to make this vision a reality?
He's very clear about the need for continued progress on both the hardware and algorithmic fronts. We need more powerful and stable quantum computers. With those larger numbers of qubits and longer coherence times that we talked about earlier.
Oh, those are the two big pieces of the puzzle.
Exactly.
More qubits to handle the complexity and longer coherence times to allow for more complex calculations before those pesky errors creep in.
Right. And then on the algorithm side, we need more specialized quantum algorithms that are specifically designed for dimensionality reduction tasks. And as we've discussed, the development of those hybrid algorithms that can seamlessly integrate with classical methods is going to be crucial.
It's all about finding the right tool for the job, whether it's classical or quantum. Schneppet's vision isn't about quantum replacing classical entirely, but rather about this powerful synergy between the two.
Right. He sees quantum computing becoming this integral part of our data analysis toolkit, adding a whole new dimension to our understanding of data.
It really is a paradigm shift. Schneppet focuses primarily on image processing, genetics, and finance as potential areas for QEDR to shine. But I'm curious, what other fields could be transformed by this technology? What other massive data sets are out there just waiting for QEDR to unlock their secrets?
That's a fantastic question, and it really speaks to the boundless potential of QEDR. Think about climate modeling, material science, drug discovery, any field where we're dealing with these massive, complex data sets. QEDR could revolutionize how we approach research and discovery.
It's exciting to imagine the breakthroughs that could emerge. This has been an incredible deep dive into Jorgo Schneppet's vision of a quantum-enhanced future. It feels like we're just beginning to grasp the potential of this technology, and the possibilities are truly mind-boggling.
Absolutely. And as we move forward, it's important to remember that this is a journey of continuous exploration and discovery. We'll need to stay curious, collaborative, and adaptable to fully realize the transformative power of QEDR.
Well said. A huge thanks to you for guiding us through this fascinating topic. And to all our listeners, we hope this deep dive has sparked your imagination and left you pondering the incredible potential of this quantum-powered future.
It's been a pleasure. Keep exploring and stay curious.
And until next time, we'll see you on the deep dive.